hear that some of you are at least still awake. So, today I have some very important news for you, which is, please do not panic. Some also useful news is that assignment 2 is now out. It walks among us. But we'll be discussing that in just a moment. Also remember, there is a weekly test that is due tonight. If you haven't yet done that, probably a good time to do that sometime soon. But please note, Giv is currently experiencing some difficulties. We've got our most senior magicians looking into it. It will hopefully be fixed soon. And also remember, next week will be Quiet Week. I'm saying Quiet Week too loudly. Quiet Week. It will be Quiet Week next week. There will be no lectures, no tutorials, no labs. You can focus on catching up, or if you are already ahead, catching up with other subjects. The help sessions are, as far as I'm aware, still running, and you can find out more details. There may even be more rostered on, so keep an eye on the course website for details. So, before we get into the meat of the lecture proper, we're really picking up where we left off yesterday, talking about composite data types, talking about memory, talking about how we can manipulate and use our own memory. But we're also going to have some more wonderful diagrams, actual diagrams this time, and we're going to have a little bit more of a look into some of the C language features that are on the table, though we discourage, so here they are, don't use them, in the same way that we saw a few yesterday. But first, there's an assignment. Ooh. So, what I want to have a quick look at, first of all, with you all, is the spec of this new assignment. It's called Intensity. And it's, I think, it's quite fantastic. I played it last night with a couple of tutors. It was fantastic. So I reckon you'll absolutely love this. This is an interesting little card game. You have 40 cards, which may give you some idea of why I have this interesting diagram here. Some 40 cards, and on each of the cards they're numbered 10 through 49, or 10 through 49. And the reason I make that distinction is because the cards have value, particularly all of these 3 cards, which I've numbered here, and particularly the 4-7, which we call the buffalo. So, oh, and of course no 2 cards will have the same number. There are 4 players. You will have a hand of 10 cards. You will swap, firstly, 3 cards from your hand to the next player. And then the game proceeds in 10 rounds, which go in the form of, I pick a card from my hand, or one of the other players picks a card, and then play proceeds. We all play our cards, and eventually one of us will win. So first of all, if I were to play, the example here is 1-7, then you must all play 1 something if you have such a card, otherwise any of the other cards you have. And you can win a round by having the same first digit, the same 1, but the highest value. But you may think, oh yes, you want to win. No, 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 no. No, 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 no. Because the scores are to the bottom. The lowest score wins. So ideally, you want to be aiming for, well, 0 by the end of it. So how do you not score 0? Well, if you have any cards of the calf set, the cards 3-0 through 3-9, then you will take a penalty. You will take points. If you play 4-7, you take a penalty, and that penalty is 7 points. So, The aim of the game is not to win. How very peculiar. And of course, once all of the rounds are over, then we score. And yes, it is the fewest points to the bottom. And what you are going to be doing is writing a player for this really quite intense game. Ha-ha! So, I happen to have a player. In fact, we've got a player for you. And if I just grab my code, I was writing some code to play around with this last night. And we've got a referee program for you. It is called, amazingly, Intensity Referee. And I can just run it, and it'll just sort of run a game. And we can roll through the log of this game, and we can see what actually happens. We see that a set of cards get dealt. Our 4 players here are named Amy, Lulu, Rat, and Morgan for hysterical reasons. The first thing you must do is the discard portion of the game, and we can see here that our 4 players are choosing cards out of their hands. Your AI must do this. You are building an AI that plays this game. Your AI must choose some cards to discard from its hand. They move to other players' hands. And then you play. So here we play the 1-1, good first hand, then the 1-7, then the 1-4, then the 1-9, and the 1-9 being the highest card in the 1 set wins. And it continues. 4-3, or 4-6, 4-3, 4-9, 4-8, 4-9 wins. At this point, we can see that one of these players no longer has any 2s because they've been forced to play a 4-5 in this hand of 2-2, 2-6, and 2-7. But the highest value still won here. So the 2-7 still wins this hand. And then some foolish person decides to play the 4-7. And the thing about the 4-7 is that you really have to have someone who is able to better that, or you take home a penalty points, which in this case looks to have been something of a foolish move. And so on through the rest of the 10 rounds, and we see that the players finish up each with 0, 3, 4, and 10, and Amy goes away. I would say victorious because winning that many points, but that's not victorious at all. And the thing about this player, well, you think this referee is pretty boring, but I can give it a player that I've written. So, for example, I have here the stub code that you're provided for this assignment. The stub code that we provide for this assignment is intentionally broken. It will intentionally lose really, really badly. Really badly, with a whole bunch of illegal moves. It will always make an illegal move and will always wind up losing miserably. But here is a better player. And it again is going to try. It's going to move cards around. It's not doing too badly. It's pretty simple, but it hasn't lost nearly as miserably. With an even better player, you could do even better again. You could conceivably win rounds, win entire games. And your AIs, they can be as simple or as complex as you like. You can spend time perfecting, tuning, tweaking, finessing your games, your style, your strategy over the next few weeks. There will be competitions, as I'm led to believe, and there will be more details of those coming shortly. And we've got a whole bunch of information here. There will be an interactive player where you can play along, and yes, there is a tournament here, and it will be players against other players. It will be you guys all pitted up against each other head to head. Question from the floor. It's not available yet. It will be available real soon. The interactive player is still being tuned. We've got a couple of bugs to iron out there still. But it's looking pretty good. It's looking pretty good when it doesn't freak out totally, which it did a couple of times yesterday when we were playing with it. Very miserable. We give you some initial code. Let's have a look at that. And this probably looks rather familiar to you. You've seen this or code of this style before. This looks very much like the stub that we gave you for the first assignment. Right down to the header comment. Make sure you fill in the header comment, please. Unless your name actually is your name here and your ZID actually is 5555555, I highly doubt that. But then again, we have gentlemen like my good friend Bob, who I can't see. Where are you? Oh, he's looking away. I see. Who also have anonymous names. So, yes, we have here selection of actions, selection of cards, hash defines for those things. We provide you a simple main. You shouldn't need to touch this. You will provide it either one of 4 options, and it will tell you either the player name, which you must choose. In this case, you would print out the name of your player. You can choose to discard. You will need to work out what the cards are and choose ones to discard. You will want to read these into an array because it's going to be no fun if you don't. And finally, here we have your routine where you must choose a card to play. This isn't a legal move under basically any circumstances, but you say, this is the move I want to make. It's very simple, very easy. You just say, here is the move I wish to play. The referee knows what cards you have because it gave them to you. And you must pick the best card, or what you would consider the best card. That's the AI. It's very simple, very easy. You probably also want to write some unit tests because otherwise you're going to have some really terrible code and it's just going to break all over the place. If you've got any questions, I believe the forum now has space for you to start asking questions about this. The spec is, I believe, up on the website. I was told it was up on the website. I'll just quickly check that. Look, it's up on the website. You can head over here to assignment 2. I believe there'll also be a link from WebCMS 3 over here. Yes, and you'll be able to go and find material there. All right. So that's intensity. Are there any questions? Yo! You can choose to spend some of the quiet week working on the assignment. You don't have to. You could relax. Probably a good idea to make a start early, make small incremental changes as you go. This is definitely not an assignment where you can just sit down and bang it out in 3 hours and it's perfect. So I would suggest starting sooner rather than later. Hello. Final exam content. Ask on the forum. But it may be useful, I would think. Yes. When is this due? The $1 million question. Let's have a look. That's very interesting. I don't see a due date. So I'm rather suspecting there will be a due date added when other Andrew realizes his mistake But 7th of May, I'm not seeing anywhere that says 7th of May here, so I don't know what's going on there. I think something may be freaking out on the course website. So it will have a due date. What that due date is exactly, I've heard from a few people up the front, might be about the 7th of May. I would treat that with a grain of salt for the moment. But it definitely will be due at some point over the next few weeks. I suspect it'll be in about 2 weeks, or 2 or 3 weeks. All right. Any other questions? Yo! How is it going to be marked? What a great question. And hopefully there will actually be an answer here. So it will... What intonation is going on here? I think the course website is freaked out. Let me try just quickly... Do 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 do. There we go. I have no idea what happened there. The course website is being uncooperative. Yes, there is a due date. There it is, Monday the 7th of May at midnight. There is indeed a Martin criteria up here. And there will be a portion of this which is your performance, how well your player can play. And we're pretty lax about this. So if you're able to pretty much always make a legal play, you're already more than halfway there. There will also be marks based on how well humans can read your code, which is quite an important thing. And we're going to talk a little bit more about humans reading your code a little bit later. We haven't yet, I believe, had assignment 1 released to marking, but I imagine that we will be exploding with rage at some people's code, which is disgusting. Just a guess. I haven't actually looked yet. So, there it is. There's your second assignment. Are there any other questions before we move on? Yo! That's a very good question, and one that I don't, I'm afraid, have a good answer to just yet. Hopefully there will be a better answer for that sometime soon, presumably when that happens. All right, any other questions? Okay, let's move on. So there's the player. What I want to talk about for part of today is a little bit more C. So yesterday I said, shh. Yesterday I said we'd reached the end of the C you need to know. Entirely true. Here's some more C that is probably useful to know, but is also probably useful to know why we discourage it very strongly. Now, yesterday we saw global and static variables are both strongly discouraged. Come on. Are both strongly discouraged. And here's some more stuff that we strongly discourage, including the keywords break and continue. Now these allow us to move control around our program. pretty much arbitrarily, although with some restrictions. There's an even more souped up version of this keyword called goto, and you are strongly discouraged from using these, and you are extremely forbidden from using goto. Why might that be? Well, it turns out the style guide has answers to all of these things. Break statements allow us to break out of loops. And it's very tempting when you're writing code in labs. This is something that I've heard and seen a little bit of the code that demonstrates this. Some of you think that when we are marking for style, when we have got humans marking your code for style, as is the case for the assignments, but as is not the case for labs and the labs and weekly test exercises, you may think, we can just do whatever we want. And that is there. I have seen it. I have seen really awful code that people have written to attempt to solve some of these exercises. And things they're doing include just randomly breaking in the middle of their code because some condition becomes false or true. Or people who just stick a random continue in the middle of their code. Continue lets us go from this iteration of the loop to the next one. And both of these are extremely dangerous. You should avoid these at all costs. And most definitely, down here, don't use goto. There's a selection of other things which become very difficult to use without break or continue. So don't use them. If you have, who went and read the style guide after yesterday's lecture? My goodness. One person, fantastic. For that one person, well done. For the rest of you, you're all miserable. You make me sad. Read the style guide, especially if you haven't read the style guide yet. You may think that your code style is the best, that your code style is the most beautiful, the most wonderful. You are the best programmer in the world. Well, let me tell you something. When there is a style guide, its word is law. And this is true wherever you work, wherever you are writing code. There will be a style guide or style guidelines. You must follow them. One of the things, and the one person who went away yesterday and read the style guide, one of the things that the style guide says, in fact, right at the very top, is come back and read the style guide every now and again, especially when we show you new things. And we saw a whole bunch of new things yesterday, and only one of you went back and read the style guide. That makes me very, very sad. You should read the style guide. Another thing that people like, especially rusted-on C programmers, but also people coming from other languages where they have been wonderful programmers writing wonderful code, and I say that with so much sarcasm I hope it hurts, is they think writing less code is better. They think writing terse code is better. And that's not true. There is nothing at all true about terse code being better. I'm a programmer. I am lazy. That laziness extends to the amount of effort I want to spend reading code. And I have had to read some awful code over not only the years I've been teaching, but also out in the wild, terrifying real world, the place where people write shit C, and in every other language too. And one of the most easily abused constructs is the for loop. And the for loop, you may think it's nice, especially if you're still getting used to writing code, you're still getting used to making sure all the bits go into the right places of your loop. Because with a for loop, it's there. It's right there. All of it is there. My initialize is before my loop. Now it's in my loop. My condition, it's there. Now it is surrounded by my initializer and my condition to step us to the next pass of the loop. And you may think, oh, this will catch the occasional I++ that I forget, or something of that nature. The problem starts to happen when you start taking liberties with what goes in each of these little patches of space. So when you start coming up with tricky conditions or weird initializers, or wonderful multi-thing steps, it is very easy to write bad for loops. Many languages avoid the whole idea of them because they are so painful to get right and so easy to get wrong. In many languages, the for loop is not just a thin veneer of syntactic sugar. There's the magic word here, syntactic sugar over your normal looping construct. In other languages, for or for each might actually give you some idea of for each thing in this collection, but in C, we don't really have that. So why bother using this wonderful weird syntax? So, we'll see a couple more bits of assorted C, which are probably a bad idea, and we'll see those in a few minutes. But I want to go back and talk about something we talked about yesterday, lifetimes and scope. Now, for those of you who weren't here, you probably would have seen this in either the lecture recordings or in the notes yesterday, but just to refresh our memory, we have this thing, we call it the stack frame, and in it we have a whole bunch of information that is important to one invocation of a function. And the values on the stack, the values in these stack frames only live for as long as that stack frame does. And we can call this the lifetime of that value. The lifetime of a stack variable is bounded by that stack frame. Yes? This shouldn't be news to you. And we saw some approaches for keeping values alive. We saw some approaches like pushing down that reference or pushing down the value and passing a reference up. Let me just show you what that means, because apparently some people were a little bit confused by it when I was just waving my hands around. Let's see what I can do with this. So, record, please. Very good. Okay. Our stack frame, we remember, is really rather boring in its structure. We have some region of space, and in it we've got a whole bunch of little boxes, little holes where values get pushed into, where values live. And if I call another function, when I call that function, it sets up its own new stack frame. So if I were to say this down here is the stack frame of main, and I were to call some function that, I don't know, whoops, let me get that right. If I were to call some function that gets me the best card to play, for instance, how How do I know where the cards are? Well, what I could do is I could have those cards down here in main. And with those values sitting down there in main, what I do is I pass a reference up to best play. This is what I mean here by pushing the value down, taking a reference to a thing that is lower on the stack, because remember, stacks grow upwards. Taking a reference lower down the stack, passing that reference upwards, making sure that thing stays alive. Some of you may think you can go even further and push this off the stack somewhere. Put it somewhere where the global variables and static variables in this world live. And I will say to those people, absolutely not. My God, you are not allowed to use global variables and static variables. But instead we give you a mechanism for asking for memory elsewhere, for managing your own memory allocations. And we give you some functions to do that. Let me just quickly show you how memory looks. We've seen this diagram before where we show you memory as this contiguous blob of space. I'm really, really good at drawing straight lines, as you can see. And we talk about our low addresses in memory and our high addresses in memory. And we saw some addresses the other day showing up when we were printing them out. But in an idealized world, this is sort of what it looks like. Up here, right at the very top, there is some magic that you never want to touch. That is where null lives. That whole region right there, up at the 0 address. That's where null lives. You're not allowed to touch it. You're not allowed to dereference it. You're not allowed to do operations around it because it is invalid. And if you start seeing some of those invalid array, pointer, or other operation errors out of DCC, be so very thankful that it's catching you doing bad things up here in this high region of memory. Then below that, we have our code. Our program has to be in memory for us to be able to run it, yes? It gets very boring if we can't run our programs. And we'll talk in 1521 in a little bit more detail about how stuff is laid out in memory and how things move around in memory. But for now, we can just work with our code lives up here. And the other region of memory we have seen is the stack. And we've seen it for basically the entire last few weeks because that's where all your variables live. That's where the stack frames live. They live piled up in the stack. Sometimes you'll hear it referred to as the call stack, and it all lives down here. And there's a couple of function calls sitting down there happily in the stack. So, if things on the stack have a lifetime that is bounded by the life of that stack frame, then I need somewhere else to put my data. And as we saw, the functions malloc and calloc give us references to somewhere else in memory. And we call that somewhere else in memory the heap. And on the heap is all of the dynamic allocations you make. And they sort of also behave a little bit like a stack, but it's a bit more complex. And again, 1521 goes into a bit more depth than that. But your heap allocations all live up there. Your dynamic allocations all live up there. And you can refer to them from in the stack. I can have a reference down here pointing me up to somewhere on the heap. That's completely fine, and pretty much every single C program in the world does this in some way or another. All right? Are we happy with this so far? Are there any questions about this? All right. So we have three functions for managing allocations that we are making on the heap, and we talked about a couple of them yesterday. We talked about malloc. Malloc's just a nice little function that lets us make an allocation. And I can say, hey, I would like some memory. I would like some space to hold some data. And malloc doesn't really care about what the data is that we store there. It just gives us that many bytes of uninitialized memory. If something goes wrong, and it could, and we'll talk a bit more about that in a moment, it will return null. Now, I don't like malloc all that much, because malloc has a couple of problems. First of all, if I want to actually allocate anything, presumably it's going to be of the type of something I have. It might be an array of integers or a structure. Doing the multiplication for how many things I want by how big each thing is can go wrong. And we've talked about what happens if it goes wrong. We also have the problem with malloc that the memory we get back is uninitialized. Yes? We don't know what's there. Tools like DCC-valgrind will yell at us about this because it's uninitialized. So wouldn't it be nice if I had a function that solved both of these problems? I wonder what that function might look like. Well, it would take two arguments. One for the number of things, one for the size of each thing. And it would return, again, a reference to that much space. Maybe it would initialize it to some useful value. I wonder what such a function might look like. Maybe like this one here, because that's exactly what calloc does. Makes us an allocation of a contiguous block of space initialized to 0, and we get a reference to that, or null if that goes wrong. I personally love calloc. I think it is a great function. It is a marvelous function. And of course we touched on a law yesterday by one of my favorite computer scientists, Isaac Newton, who said that for every allocation there must be an equal and opposite free. Every time you request some memory, you are responsible for making sure that memory goes back. That memory is returned, and free is our mechanism for doing this. It releases the memory that is associated with one of these references. It's very important, of course, to give it exactly the same value it gave you when you allocated. And we can actually go so far as returning references to things on the heap from functions. That's one of the great things that we've been trying, that's the great problem we're trying to solve here. We want references to memory that will outlive our function. And it just so happens, here is a mechanism, these three functions, for doing that. One of the things, of course, that we need after that is, well, maybe it's no longer my responsibility to release that memory. Maybe I've given a reference back to some allocation. And usually such a function will tell you in its documentation or elsewhere that you must release its memory somehow. And we could have either functions where they're relatively simple allocations, we can just use free, or they might be more complex, and you need a dedicated function which destroys that allocation. So why is it that we have Newton's third law of memory management? Nobody knows what the other two are, by the way. I'm not sure why it's Newton's third law of memory management. But memory is finite. You don't have infinite gigabytes of memory in your laptop. That would be nice, especially for programs like Chrome. But that's not something we can do. We have to give back the resources we use. And it just so happens Chrome is really bad at doing that. Memory is a finite resource, and especially when we're building long-running programs, as we start to head towards now, you need to make sure your program is appropriately managing its memory. For really simple programs, which maybe run for a second, then okay, the operating system sort of looks after us. But if your program is going to be hanging around for, say, hours or days or weeks or months, then it's highly important. And you don't believe me when I say months. A piece of software that I'm responsible for fell over yesterday after having been up for a little bit under 9 months. It didn't leak any memory because I was very, very careful when writing it not to leak any memory. A tutor up the front is reminding me that I've cheated a little bit in doing that, but effectively I didn't leak any memory. Because it's a finite resource. I don't want my program to fall over in 6 months and say, oh, I ran out of memory. But what if that happens? How do we deal with the problems of things going wrong? There's a whole raft of functions whose responsibility it is to get our programs out of trouble. And usually the only mechanism for getting our program out of trouble when you run out of memory or when you can't access something is to exit. There's nothing your program can do more than that. So here we have one of my favorite functions, someone went wrong, couldn't allocate. And what it'll do is it will take the program down. And it will say, I couldn't allocate some memory, for example here. Remember, calloc or malloc can go wrong. They will return null if they couldn't make that allocation. And I can catch that by saying, if I got null, I bail out. There's a number of other mechanisms for doing this, like p-error, like fprintf, like asserts, like aborts, and so on and so forth. Pick one of those and stick to it. What a good question. The question there was, if I make an allocation and I can't satisfy the entire allocation request I've made, will it still give me back some memory? Well, that wouldn't be very useful to me, because I haven't got the amount of memory I asked for, so I can't really do anything with the 99, say, out of 100 places that I've requested. Because calloc and malloc, there is a contract between you, the programmer using these functions, and the libraries, the standard C libraries, the operating system, who provide these resources and services to you. And the contract goes, you, the programmer, will use this function, will use the resources we give you, will use the services we give you without destroying them. You will use them as they're documented to be used. You'll use them in valid, reasonable ways. If you do something invalid, that's on you if something goes wrong. And part of that contract is, well, sometimes we can't provide you that service. Sometimes we can't provide you those resources, and under those circumstances, well, there's really not much you can do, because you no longer can uphold your end of that deal. If I ask for 10 things here, 10 integers, and I get space for 9, and then I write expecting to have permission to, or an ability to write into that 10th place. Because that is what I asked for. I asked for 10 integers. That 10th place is something that I expect to get. So if I don't have it, well, that's not upholding the contract that calloc and malloc and these functions hold. Another thing that I should also briefly mention, just quickly, did that answer your question? Yep. Fantastic. Another thing that I want to quickly mention is something that you will find if you use my good friend the internet and my worst nemesis, really old textbooks that have never been updated in 30 years, which is sometimes there are things that are wrong in this world or things that have changed. And one of those things that has changed is types. C has gotten, or C compilers, the things that actually have to look after data about types, these have gotten a lot better at interpreting type information. Now, some of you who remember there will have spotted, in fact I'll show you, the type signatures of calloc and malloc. And they look very similar. You give them some numbers in, and they give you a reference. What type of reference? A reference of type void. And we've seen void before. It's the value for where there just isn't a value. So how can I have a reference to that? Well, it turns out I can. It's perfectly valid to have a void reference. But I can't dereference it. Not as a void, anyway. If I instead take this value, and as I do in this piece of code here, cast it into an integer reference shaped hole, then, okay, now I can deal with a set of integers. The problem that some particularly older C compilers, compilers that were old when I was born, is that they couldn't deal with the types very well, and so you would explicitly have to sort of do a Jedi mind trick on them. This isn't the type you're looking for. And there it is. This thing here is called a typecast. And you should almost never do this. And this is definitely a case where you don't need to, and therefore shouldn't do this. You will see this especially on the internet by old C programmers who've forgotten how to program properly anymore. And they write terrible code and they tell you to make typecasts. Don't do it. Don't make typecasts. C is a language that has enough types to be able to let you make statements like this. I can request a reference to a selection of integers. I can request 4 integers. Which begs the question, how do I access them? How do I deal with these 4 integers? And we'll talk a little bit more about how we deal with those 4 integers in a bit more depth after the break. And also we'll go back, revisit structures, and see cool things to do with them. So let's take a break, a little bit late, 10-minute break. After it, we have more on working with memory and structured data in C. Alrighty, let's get moving again. If I can ever remember how to use a computer, that will be the day. Alrighty, welcome back. I hope you did actually all stand up and move around a bit. So, ooh, pretty pictures. This is my substitute for Andrew's hair. As you can tell, I don't have any rainbow hair. So this is my substitute, pretty colours. So one of the questions I got a whole bunch during the break was, why? Why have I just spent an hour rambling on about casting and memory management and values moving around? So let's actually cause something to go wrong. Let's go and play around with that. So yesterday we saw a bunch of examples where we had a value, we returned it from a function, but because that value didn't live long enough, it was garbage. Yes? Let me grab those examples from yesterday. So we started out by taking an array in a function. Yes? And then we printed this array out and then we returned it. And we saw what happened when we did this. And if I just quickly recompile these, A, the compiler yells at us, yells a warning, but B, when I actually try and run it, we see our values are clobbered, yes? This is the problem we're setting out to solve. This value hasn't lived long enough for it to be useful. Yes? Lifetime is a great way of reasoning about when values are useful to us, when we can do stuff with these values. And it turns out this didn't live long enough, and it was fair game when the stack frame was torn apart by wolves. It was fair game to just write garbage over it. And there could be all kinds of interesting stuff in this space, but it's not interesting to us. Yo! How come some of them remain the same? Is that a coincidence? Yes, it is entirely coincidental. Yeah. So in this case, what happens if I GCC it? GCC usually does different weird things. So GCC produces us a different result again. So with DCC, the first two are preserved, the next two are garbage, the next two are preserved, and then all the rest are garbage. In GCC, the first, what is that? 5 are garbaged, and then the remainder are left the same. And this is just a quirk of how GCC and DCC set up the stack frames for the new functions. So where might those new stack frames be? Well, directly above the old ones, which is where this value is, so possibly this has been overwritten by part of a stack frame for someone else's function, which is kind of awkward, and we definitely don't want that to happen. So we then showed you the next approach, which is that we push that reference down. And a few people said, well, why don't we do this? Why don't we just do this? Take all of our arrays and push them into main. Well, why not? Well, I would have a main that's about 5,000 lines long, full of arrays that I then have to pass, say, 5 function calls deep to where it's actually used. And that's not nice. I don't like it. So we saw this as an approach. This works with very simple programs, very small programs. We can do that. We can push those values up and out of the way. Or we can put them somewhere else. And this is something we saw yesterday, and we'll talk about a bit more now, which is that I can make a dynamic allocation. This allocation lives somewhere else in the system. It doesn't live where we want it, it doesn't live on the stack, which is where we don't want it to be. We want this value to stay alive for long enough that I can take this value, do something with it, and then give it back to the function that called me. And I can't do this if the value dies. I have to put that value somewhere else. So that's what I've done here. That's what malloc lets me do. That's what calloc lets me do. That's why we're doing this. And so far all of these examples have been about arrays and passing arrays around, because that's something we've seen. So why don't we try this with a structure? Now it turns out with a structure, things just sort of work. Structures are sufficiently simple values that they can just be copied. And that's not great. I mean, it's kind of useful, but that means now we may have to return, well, we saw one of the structures yesterday, well, that's 76 bytes, but we could see conceivably structures of hundreds, thousands of bytes in size, and we don't want to be having to copy that around all the time. As just an efficiency thing, it's not useful for us to have to copy those thousands of bytes every time we want to do something. So what we do instead is we can put those structures on the heap as well. Let's just quickly recap though. Structures are a great way of grouping together a bunch of data that is related but may have different types. Yes? Arrays must all be of the same type. Structures let us have things of different types. A whole bunch of different things with names, with different types. Very useful. Yesterday I mentioned typedef. And I said typedef struct, this is just a thing we use. Let's just pick this apart. That's really illegible on this projection. Well done, projector. Let me grab this and dump it into a different text editor. Here is what I've got. I have a typedef of some existing type. Yes, this portion here, some existing type, and it can be arbitrarily complex. It could be a whole pile of interesting stuff. It could be ints, it could be a whole structure allocation with a star on the end. All kinds of lovely stuff. And I can take that and give it a new name. Hopefully a more convenient name, but not always. For instance, okay, what if I were to do something like typedef some existing type? What's an existing type we know? How about int? And let me just give this a nice, awesome name. Now I can use this type wherever I want, right? So for instance, main. What type has main? Well, clearly main is of type Andrew. Oh, sorry. There's two arguments that main has. They are Andrew, argc, and char*, argv. And let's say I could declare some integers, Andrews, in this function. And I might want to return one of them. And this is taking it a little bit further, but this illustrates my point very nicely. Sometimes typedefs aren't always wonderful, but sometimes they are. This is one of the cases where they're not particularly wonderful because this type makes it really hard to read. There's actually, I should just mention as a fun little side note, there's a competition called the International Obfuscated C Code Contest, or IOCCC. And the purpose of the IOCCC is to abuse C as much as we can. Twist it and bend it and break it to write the most mangled and ridiculous code it is possible to write. Typedefs are useful for that because you can take convenient, nice names and make them absolutely illegible. All right. So there's our typedefs. So we can create better names. We can create more meaningful names. For those of you who have been switched on and reading the course forum, you will remember, especially with the first assignment, it was incredibly important to use meaningful names. Names have meaning. Words have power. Words are useful. Actually, giving things meaningful names makes your programs better. Your program ceases to be this mess of random characters, but now you're describing things that are actually happening. You're describing values moving through a system. You're describing the way the data changes, the shape, the nature of those values. Another thing we can do with typedefs, of course, is to hide the fact that this might be a structure or an array or something of that nature. And we'll talk a little bit more in a couple of weeks about how far we can take that. Because we can take it a very long way indeed. And of course, I'm lazy, I can type less, excellent. But of course, within reason, the things that I'm typing still need to have some meaning. The other thing that I mentioned was structure tags. Now, structures all have tags. Sometimes the tag is generated by the compiler and just sort of hallucinated together, but most of the time you're going to give the structure a name. Where did my editor go? There it is. So here is a structure with a tag. And back here, there we go. This tag means nothing to the system without that structure tacked up the front there. So I can't just refer to this type as tag. I have to refer to this as struct tag to be able to refer to it. And this is why we wrap this with the typedef. This is why we take our typedef and we come up with better names, more useful names, and because this entire structure is effectively a type name, I can make that have a better name. And now, yes, I can refer to this as just tag. You'll also notice up here I've carefully chosen a name which is the name of my type, the name that I want my type to have, with an underscore on the front. This is a useful practice to have just to avoid confusing older, sloppier compilers. But these are perfectly valid things to have. All right. So let me take a side note and talk about something completely ridiculous. Now, many of you, I'm sure, have seen maths in any way, shape, or form. Who has never in their life seen any maths at all? I see a disturbing number of hands raised. Good, good. So some of you probably, in fact I think by this point you probably all have seen to some extent complex numbers. Complex numbers are, I think they're quite beautiful. You probably think they're the bane of your existence. If you're doing engineering or physics or any of those hard sciences, in a couple of years you'll come to hate them. But here for the moment is an interesting little fact, which is that in this form of a complex number, I have said here is a name, here is a thing with a name, and I have said that is this value, this x, plus some value y, and there's a little bit of stuff left over which we'll ignore for the moment because it's not interesting. Now, mathematicians see this as formulae and a whole bunch of cool rules. I, as a computer scientist, see this as data. Because remember, as computer scientists, as informaticians, your art, your science is that of data, of information moving around the system. So when you see mathematicians going, ooh, 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 look at my cute formula, what you want to be doing is going, yes, but where's the data? Where's the information? And it's all buried away in there. So I could conceivably take this and make it a structure, because this is a piece of structured data. So let's say I had such a structure. What might that look like? It's going to be, of course, a struct, and I'm going to call it complex, because I'm extremely bad at choosing names. I choose obvious names or simple names, and complex is such a very simple name. So, what am I going to put in this structure? I mean, we can go back and look at our definition of the number. We know that such a number has the form something is represented as something plus some other thing. I see two useful bits here. I see this x here, this y here. I want to put them in a structure of mine. All right. So I want to put these things in a structure of mine. All right, so there's a nice, obvious, simple structure. The problem is that we want good names, yes? And I don't like x and y as names here. So maths people, what are better names for these things? That was the most depressed, miserable rendition of that I've ever heard. Yes, real and imaginary. I have a pain in the diodes all down my left side. So, I have these things, they have actual names. I'm a programmer though, I'm lazy, so let's just leave that bit off. Real and imaginary. So we'll leave it like that. Now, we know how we would go about constructing a complex number, yes? Nice and easy. If I were to write this in a function, and let's just wrap in the void here, and let's return some 0. With this type here that I've defined, what would I do to use it? I just say complex. Some complex z. And what values does it now have? It doesn't really have any values. So I now need to give it some values, and I can do this in a couple of ways. One way we saw yesterday was to use the name dot field name notation, and we'll do that for the moment. So I can say z dot real is, I don't know, 1.0. And z dot imaginary is 0.0. This is a nice, boring, complex number. In fact, some mathematician will probably go, that's not even a complex number. Yeah, it is. Yeah, fine, all right. I could just have one double to represent this. So, I have my complex number. I have this box that holds these values, but that's not all that useful to me. What might be more useful might be some functions that manipulate complex values. Yes? So let's have some functions that manipulate complex values. A manipulation that we might want to do with complex values might be to add two of them together. So if I were to write a complex add function, what type am I going to have when I return? What type am I going to pass in, and what type, in fact, what types am I going to pass in? Because add is a two-sided function. It needs two values to do anything useful. So, what might this function take? It's going to need a complex number and probably another complex number. So, let's give it them. I'll call them complex A and complex B. There they are. So that's all very nice. What am I going to give back? A double? Complex add. If I take two complex numbers and add them, my result's going to be complex, yes? I'm not going to suddenly lose half of my number. So I'm also going to need to return a complex value. Because this is a structure, because this is simple, I can just return it. Now, to add two complex numbers together, what do? Nice and simple, yes. I just take my sum as the sum of the real parts and the sum of the imaginary parts. So we have another notation I'll just introduce at this point for referring to referring to structures, which is to, in a set of curly braces, and remember this is a set of curly braces, so the indentation rules apply, lines should be indented another stop. The real part of this structure is the sum of the real parts of my incoming complex numbers. A dot real plus B dot real. And the same for my imaginary part. A imaginary plus B imaginary. And now I can just return that. All right? If I was feeling really tricky, I could avoid even defining a variable here and just return that structure in basically the same shape as I've declared it here. But both of these are valid ways of referring to structures. If you're feeling really tricky, you can even omit these names and rely on the order of the structure. The problem with that, of course, is that means you've got to remember something. I heard someone say the magic R word, readability. I have no idea I can probably guess, given this is complex add, but if I were to implement, say, complex multiply, these parts become really difficult to keep track of really quickly. So we want to optimize for the programmer. Yes? This is really important, and this is something I alluded to in the first part. Style guides are not there to make your life miserable. That's not their goal. The style guide is there to establish a common language between you and other people you're working with. If I were to inflict upon you now a group assignment, which I might, if I were to inflict upon you a group assignment, one thing that will probably wind up happening is that you'll probably, if you didn't have a style guide, you just write whatever style code you want. And you'll be able to tell who wrote whose code. Because this code has, say, tabs to indent, this code has, say, 3 spaces to indent, and it's all just an awful, miserable mess. Style guides are there to make it readable, not just for you, but for the people you're working with. In this case, the people you're working with are also the core staff, the tutors, the lecturers. We've seen pretty awful code, but we would prefer to be reading much nicer code. We would prefer you to write nice code anyway. And I'm not going to say this style guide is perfect. This style guide has bugs. Every style guide has bugs, because every style guide is, to a certain extent, just an opinion. Just someone's opinion, but in this case, this is an opinion where, unfortunately, you have to follow it. Because it's a little bit more than an opinion when you actually have to follow it. It is now, this is the rules. These are the guidelines. And one of the bits of the spirit of our style guide is to write code that is readable, and this is not readable. You can guess, but now you're having to guess. This is way better, where I'm explicitly spelling out the various parts. I'll just save this for the moment. Whee, come on. Come on. There we go. All right. So I suggested we might want to write a complex multiply a moment ago. So how might I do that? How might I write a complex multiplication function? Well, we'll start with all the boilerplate. Once again, we're going to take in two complex numbers. We're going to return another complex number. So I could say complex multiply complex A by complex B. So what's the rule for multiplying complex numbers? Okay, let's break this up a little bit more. Let's say, what is the real part going to be? Oh, I'm sorry. Yes, that should be mult.re. Oh, say that again, but slower. So A is real times B is real minus A's imaginary part times B's imaginary part. Yeah? Let's use our other syntax as well while we're here. So our real part is that. Our imaginary part is a little bit more complex. It's B real times A imaginary plus, I'm hearing half a dozen people muttering their way through the formula in different orders at different speeds. So someone want to be our guinea pig and say what B imaginary times A real. All right? Cool. So I now have two functions that add and multiply complex numbers. Lovely. So let's actually, the first thing that I'm a little bit anxious about is the fact that we've written functions, and I've written a bunch of functions where a bunch of students have just yelled out half of the function. So the first thing I want to do is I want to write me some tests. So how would I test this? I'm going to throw me some asserts. So what am I going to assert here? Let's say, let me just grab these prototypes and put them where they're more visible. Why is this mouse so awful? It's like someone stuck. Oh, there we go. Okay. So there's my functions. How might I go about testing these? I want to write some tests for, say, complex add. How do I write good tests? Yeah. You've sort of hinted at the direction I want to go in here, which is that I want to come up with something that I know to be true. Yes? Remember when we were going through testing a bit earlier in the course, we're talking about testing being something that we know, then our code in the middle, and then something that we know. The only unknown is the bit in the middle, and that is the bit we want to test. We want to check that it's producing that result as we go through. So that's very nice. Let me just quickly graft up a function that turns two doubles into a complex before I get too much further here. I want a way to just create a complex number. And maybe I should have a function for that. So let's do that. Some complex number being two doubles. But I'm going to make this interesting. Let's make this return something that will live longer than the structure would otherwise. Because these structures so far have lived on the stack, yes? This structure here, this is on the stack of complex add. I would have to copy this out of the stack of complex add to wherever it's being called. This complex multiply has the same problem. It's on the stack of complex multiply. I'd have to copy it. And, you know, these are small structures. These are 8 plus 8. These are 16-byte structures. But copying this structure over and over and over and over and over and over and over again, that's going to take time. So instead, let's make a complex number in a dynamic allocation. So how do I make me a dynamic allocation? Good grief, have we all forgotten the first half of this lecture? Malloc or calloc? Yeah. I'm going to use calloc because I'm lazy. So some new complex number C, which is an allocation of one thing that is how big? Well, I know it's 16 bytes, but how do I know that for sure? How do I know how big a data type is? Yeah, I use my good old friend size of. And I ask for the size of the complex type. This is something, I'll just quickly make a quick note on. This is something that I have seen so many times. Where people do something like this. Now, one of these things is not like the other. A complex star. How big is a complex star? It's a reference. How big's a reference? Well, every reference is the same size. On this system, it's 32 bits, which is 4 bytes. So there's another 12 bytes there that I'm now just going to randomly write over at some point in the future when I do some sort of arithmetic operation on the value that I'm storing here, yes? Especially later on in the course you will see this, so be careful, don't do that. The other thing I should check here is that this allocation succeeded. Every time you make an allocation, you should check, because there's nothing more embarrassing than this going wrong, you stabbing that allocation, and then, like a creeper in Minecraft, it just blows up in your face and takes your program out with it. So, what am I going to check for? I want to check that something has happened here. What happens if calloc goes wrong? What do I get? I get null. Yes. So I want to check that C is not null. If it is null, then something has gone horribly wrong, and I want to bail out of this program. And we had a bunch of functions to do this. I like Okay. Now, what I have here is a structure pointer. Yesterday we saw 2 new bits of syntax for dealing with structures. One of them was dot, One of them was arrow or stab. And what I'm going to do is I'm now going to, because this is a structure pointer, I'm just going to stab this and chuck some values in here. C arrow real is real. C stab imaginary is imaginary. All right? Well, that's all I need to do in this function. I've set up my complex number, so I'm now just going to give it back. All right? So what I've got here is a function that creates me a new thing, sets that thing up, and gives it back to me. This is a pattern we will see again and again and again. You'll see this shape of function again and again and again as we move through the course. A function that makes an allocation, sets a couple of values, and then gives that back. Let's now just quickly modify our functions to deal with this fact. So instead of returning me a complex, I'm now going to return a complex star from complex add. And I'm going to take in two complex pointers. Now, I can't just chuck a star up the front of complex sum here, because that doesn't make sense. Instead, complex sum is now just a call to new complex. And it's going to take its real part and its imaginary part and give that back. Another approach we can use while I'm thinking about such things, when we are dealing with structures, we saw that we could assign from a structure using this designated initializer notation, which is the thing with curly braces and dotted names. And I can do this with structure pointers as well. So, for this C, I have to dereference it first. So now I have a structure that I can work with. And this is now a complex which has a real part of real and an imaginary part of our imaginary argument. And I could just split this into two functions, one that just allocates and one that actually puts the values in. And now I could use the allocating version of this and have something that looks like this in my function. So instead of returning my sum, I'm now returning some new complex number. Yeah? And I'll do the same with complex multiply. I want to add, instead of just straight up structure values, I want to pass structure references. And I want to pass, again, these values back to new complex. And there it is. All right? So, what else do I have to change in these functions? Because there's a whole bunch of dots going on in these functions. So I need to change all of these dots to be arrows as well. All right? Okay, given the time, which has suddenly snuck up on us, let's stop here. Remember, there is an assignment that has now been released. You should go and read the spec. Remember, there is a weekly test due tonight. You should probably do that if you haven't done so yet.